Okay, welcome to part one of our lecture video series from Monday, May 5th. It is Friday, May 5th. Wow. Okay, part one, Friday, May 5th lecture, where we're going to practice applying the ideal gas law and also a bit of Dalton's law of partial pressures. So let's look at this warm-up question. This states that we have two glass bulbs that are connected via a stopcock, meaning that we can close the bulbs off from one another, or we can open the stopcock and then allow these bulbs to interchange particles freely. So we have these two glass bulbs, the volumes of which are known, and they are filled with the following gases. So let's say that we have hydrogen gas in the bulb on the right. And let's say that this is at a temperature of 20 degrees C, and the pressure of hydrogen that this particular bulb has been pressurized with is 100 kilopascals. And then let's say in the other bulb, we have, let's see here, why not helium? And the initial temperature of helium is also 20 degrees C. And the pressure of helium in the bulb on the left is 230 kilopascals. Okay, so let's break this up into a couple of pieces. So let's start with the first question, which is, what is the total pressure? No, let's do it this way. What is the partial pressure of each gas in the bulbs when the stopcock is opened and the gas is fully mixed? All right. So let's think about what is changing and what's not here. So originally, the volume of my hydrogen gas before the valve is opened is 4 liters. And before my valve is opened for my helium gas, my volume is 1 liter. Now, once this valve is opened, the total volume, which will be a new volume, is going to be 4 liters plus 1 liters, which is 5 liters. So it looks like we have volume that is changing. All right. Let's look at our temperatures. So we started at 20 degrees. We have 20 degrees also for our hydrogen. We were not told that these gases react and thus evolve any heat or have any enthalpy of reaction. So we are going to assume that the temperature is constant. At 20 degrees C. Okay, we've got pressures. So the pressure of hydrogen gas is going to change from 100 kilopascals because there's going to be a change in volume. Same deal with the helium. So since the volume is changing, pressure changes, because we know that pressure and volume are related in an inverse manner. Okay, what else is changing or perhaps not changing? So what else is constant? Remember, when we're talking about the pressure of a gas, we have to consider not just the volume at which the gas occupies or the temperature at which the gas exists. We also need to consider how much gas we have. So again, since we weren't told anything about like a reaction happening that might change our quantities of each of our gases, we have the moles of each gas staying the same, right? We are not, once we've opened this stopcock, adding any more gas to the system. We are just opening and allowing our original quantities of gas particles to mix. So we've got volume changing, we've also got pressure changing, temperature is constant, and moles is constant. So I think we should probably split this up into two different scenarios. Like, let's look at what's happening when the helium gas mixes, and let's look at what happens when the hydrogen gas mixes. All right, let's start by writing out our ideal gas law. So remember, I like to write the ideal gas law as PV over NT is equal to R. And let's see here. I know that I am going to need to think about what is changing as a result of my volume changing. So this is also going to be equal to, let's call this P1V1 over N1T1 is equal to P2V2 over N2T2. So I'm trying to figure out how my pressure changes, right? This is what I'm trying to figure out is the partial pressures. So since I want the partial pressure, I need to think about how my pressure changes. So I need this. I know how my volume is changing. I know what my temperature is, right? My temperature is constant. However, what I don't know is I don't know the moles of gas that I have originally in the helium side of my bulb. So my first task is I need to figure out the moles in the bulb, because while that's going to be constant, I do need to know what this value is. I don't have it. So let's start with our conditions for helium before mixing. So what are initial conditions? We have a pressure that is 230 kilopascals. We have a temperature that is 20 degrees Celsius. And we have a volume pre-mixing, looking at our helium, of 1 liter. So 1.0 liter. Okay, I know my gas law constant, which is 0.08206 liter atmospheres per mole Kelvin. And if I'm going to use PV over NT equals R to solve for N, this is going to become PV over RT is equal to N. And because my R is in units of liters times atmospheres per mole Kelvin, then I better have a volume in liters, which I do. I better have a pressure in atmospheres, which I do not. And I also need my temperature in Kelvin. So let's real quick convert between kilopascals and atmospheres. So by definition, 1 atmosphere is 101.325 kilopascals. So we have to make a division. So 230 divided by 101.325 gives me 2.2699 atmospheres. So this is my initial pressure. Okay, temperature. I need to add 273.15 to my Celsius. This becomes 293.15 Kelvin. And my volume is already in liters. So let's now use this equation to solve for the moles of gas, specifically of helium, that are present before mixing. It's going to be the same as what's found after mixing, but we need this quantity if we're going to try to solve for our new pressure. So moles of helium, this is going to be my pressure, which was 2.2699 atmospheres times my volume over my gas constant times my temperature. All right, so let's figure out what that is. So I get 24.055 in my denominator. And when I do this division, I get 0.11220 moles of helium. Okay, let's do the same thing for our hydrogen. So P1V1 for hydrogen over N1T1 is equal to R, which is also equal to P2V2 over N2T2. So let's figure out the moles of hydrogen in the bulb before mixing. So at initial conditions. All right, so the pressure of my hydrogen gas, I think, was 100 kilopascals. So 100 kilopascals, and I know that I'm going to want that to be into atmospheres. So let's go ahead and do that conversion real quick. So 100 divided by 101.325, 0.98692 atmospheres of pressure. Temperature is also 20 degrees, which is also 293.15 Kelvin. Volume before mixing is the volume of the bulb containing my hydrogen, so that's my 4 liters. And of course, we know R, 0.08206 liter atmospheres per mole Kelvin. So let's solve for moles using our rearranged version of the ideal gas law. So this is going to be 0.98692 atmospheres times 4.0 liters over 0.08206 liter atmospheres per mole Kelvin. It's our gas constant, times now our temperature, (293.15 Kelvin). All right, so let's see here. Putting this in my calculator, which I really think you should be doing the same. So we've got 0.98692 times 4 divided by our denominator. I get 0.16411 moles of hydrogen gas. Okay, now why is this useful? Let's look at what we are asked for. We want the partial pressure of each gas. The partial pressure of each gas. So let's see here. I need to figure out the pressure after mixing for my helium and my pressure after mixing for my hydrogen. So this is why I needed that moles. So let's see here, pressure after mixing. So this is P2 V2 over N times T, where N and T are constants, is equal to R. So if I want to rearrange to solve for P2, then this is going to be nRT over V2. Okay, I know my N, that is what I just solved for above, 0.11220 moles of hydrogen gas, times R, liter atmospheres per mole Kelvin. Our temperature was the same, so 293.15 all over V2, and let's remind ourselves V2 is something that has changed, right? Once we've looked at after mixing, we're looking at a new total volume of 5 liters. So we have to account for that here. Okay, so let's do this calculation. So 0.11220 times 0.08206 times 293.15 divided by 5. This gives me a pressure of 0.5397 atmospheres of, this is our helium. And let's do a sanity check. So we know up here, we said that pressure and volume are inversely related, meaning that as the volume goes up, the pressure should drop and vice versa. So thinking strictly just about the helium, we saw that since the volume increased, the pressure should have decreased. So let's check on our pressure. Right, our pressure was originally 2.27 atmospheres, and now it's about half an atmosphere. So this is something that makes sense. We've checked that we are sane, rational people. Not always true, but today, at least right now, in this problem, it is. Let us now do the same for our hydrogen. So again, we're going to use P2 is equal to nRT over V2. So for my hydrogen, we just solved for the amount of moles of hydrogen that is in the system. This is unchanging. We're just letting these gases mix, so all we're really doing is changing the volume. All right, this is now times 0.08206 liter atmospheres per mole Kelvin. I always do this. I never give myself enough room. So I'm going to just move that over here. Okay, times T again. This is our 293.15 Kelvin. Over V2, this is that common volume of the new fully mixed system. So let's figure out what the second or new final pressure of our hydrogen is. So 0.16411 times 0.08206 times 293.15 Kelvin, all divided by 50 liters. So this is 0.7890 atmospheres of hydrogen after mixing. So we have our new pressure of hydrogen, and then we also have our new pressure of helium. Okay, let's check again for sanity's sake that our pressure for our hydrogen went down. So originally our pressure was 0.9 atmospheres. Now it is 0.7. All right, so this makes some sense. That was part A. So we'll come back and do part B in the second half of this problem. So see you then.